Okay, hi everyone. Thanks for coming to the talk. So this is a quasi-random approach to matrix spectral analysis, joint work with Michael Ben-Or. Okay, so for the overview, I guess with all these talks, I can kind of skip here the first bullet. There's no need to explain the importance of finding the eigenvectors and eigenvalues of a matrix. Usually, we get eigenvalues that are hard to represent, maybe irrational. So when we talk about spectral decomposition, we usually refer to the approximate version. So we define this ASD, approximate spectral decomposition, as the following problem. You're given an n by n Hermitian matrix of bounded norm, and you want to find a bunch of vectors that are each of them is close to some eigenbasis of the matrix. Okay, so that's ASD. In terms of previous results, well, there is obviously the power method that gives you the top eigenvector and pretty quickly. There's the QR algorithm, which is kind of the power method on steroids. It gives you all the eigenvectors in time, which is n to the omega plus 1, where omega is your favorite matrix product constant. And then there's subsequent work. There's Pan et al., which reduces to n cubed. And then finally, Demel et al. Reduced this spectral algorithm to time, which is n to the omega up to logarithmic factors. In other words, for all we know, it takes the amount of time that to multiply two matrices as it is to decompose it to its eigencomponents. Okay. Since this is a very practical problem, you can also talk about parallel algorithm. Then there are two works, one by Sankey and the other one by Bini, Pan, and Reif, that give you a log squared n time parallel algorithm that runs in complexity n to the omega plus 2 and then n to the omega plus 1. So these are parallel algorithms. An important definition from the work of Demel et al. Is the notion of stability. So we have a machine that computes for us the eigendecomposition of a matrix, but we also want some practical constraint. We want our basic arithmetic atoms to be kind of independent of the input side. We don't want them to grow too fast every time we need to scale up the input. So that's called stability. You want to run on, say, logarithmically many bits in arithmetic precision and still get an inverse polynomial error in the result. So then I can ask, well, are parallel algorithms stable? So since the question is there, the answer is obviously no. These two are not stable. In other words, you need to kind of track an exponential precision to your arithmetic, or else you cannot control the error at the output. So that's the problem. So until now, for all we know, parallelism comes at the cost of stability. You can choose one or the other. And what we show is that there is an NC2 algorithm, takes times log squared n, and complexity n to the omega 1, and the upshot is that the algorithm is stable. Okay. So here's the high-level view. So it's inspired by quantum algorithms, which essentially means we're going to exponentiate a matrix pretty soon. So brace yourselves. It's based on sampling eigenvectors, like the power method. However, contrary to the power method, we're going to treat all eigenvectors equally. So there's not going to be any eigenvector supremacy here. Yeah. The key machinery here is analysis of residuals of integer multiples of eigenvalues as a low discrepancy sequence. So you may want to take 1 second to stare at this sentence. I'm going to parse it over and over again throughout this talk. So we're going to take the eigenvalues, we're going to multiply them by integers, and we're going to look at the fractional part. And we're going to analyze that sequence and how well it mixes on the unit circle. Okay, so here's the strategy. It's going to be an additive power method. So we're going to take your Hermitian A, we're going to exponentiate it, so e to the IA, and now it's a unitary matrix. And we're going to define a filtering process F that takes in U and extracts the eigenvector of U whose eigenvalue is closest to the number 1. And then we're going to take that same F, we're going to apply it to a random integer power of U. So now U to the m. And our main lemma would be that this actually extracts a random eigenvector of U. Okay, so now suppose you have this kind of machine that you kick it, and it spits out a random eigenvector of your matrix U. Now, it's obvious what we should do, right? We should just have many copies of that machine and run them all in parallel, and we get all the eigenvalues by just coupon collecting everything we need. The upshot of this is that all matrix products here are unitary, so our filtering process is essentially a polynomial in unitary matrices, and unitary matrices are kind of the best conditioned matrix one can hope for, right? So this implies stability. So we get this somewhat for free. Okay, so what is this additive power method? So it's quantum inspired. What is the quantum inspiration here? It's the quantum phase estimation. So what is quantum phase estimation? It's a quantum routine. It's a quantum circuit that gets an oracle description of some unitary matrix and an eigenvector of that matrix, and it approximates the eigenvalue corresponding to that eigenvector. That's phase estimation. And it has proved to be useful in various contexts. For example, Harrow et al. At 2009, they use phase estimation to get an exponential speedup for solving linear systems of equations under certain conditions. And then Amnon Tashma in 2013 used a space-efficient implementation of this routine of phase estimation to solve linear systems of equations in BQL, in quantum log space. So we can do this quantumly in log space. Classically, we think we can do with no less than log squared n. In this work, we're going to just simulate quantum phase estimation as a post-selected version, and that will be our filter. So with all this wording, let's just see the algorithm. So what does filtering do? So we exponentiate the matrix, we take a random vector, and then, oh, cool. So we're going to iterate until we hit this condition, which means you're close to an eigenvector. We're just going to take our v, add to it u times v, and then normalize. And do this over and over again until we hit this convergence condition. That's the entire filter. So let's see, what does it do? Well, when you exponentiate a matrix, you send the eigenvalue lambda I to e to the I lambda I. And then when we add v to u times v and normalize by v, this is what happens. If you look at the eigendecomposition of v, so v is equal to sum of alpha I vi, where these are the eigenvectors of u or a, then each eigencomponent alpha I is attenuated by a factor which is 1 plus the cosine of lambda I to some power. So essentially what happens is that if you have your eigenvalues sitting there on the unit circle of the unitary, then the one that's favored is going to be the one who's closest to the number 1. So this, we're going to crown this as our king. Okay? So now we're going to level the playing field, right? We don't want to favor the number 1. It has no special meaning to us. So let's do with more randomness, right? So we have a black box that you kick it, it spits out the vector with closest to the number 1. We want something that does something uniformly, so we take our previous procedure, that's the black box from before, which is f of u, and we're just going to add a parameter m here. Okay, let me just run this again. We just add u to the m instead of u, and then we're going to feed this random integers. So m is going to be a random integer. We're going to use it with u to the m. And how does this work for fixed m? Well, let's track again. We send lambda I to e to the I lambda I. And step D, we add v plus u to the m times v and normalize. And if you track the behavior of the coefficients, you get that each of them is now attenuated by m lambda I, not lambda I. Okay? Not much difference, but the point is, now the winner is an eigenvector whose eigenvalues mth residual is closest to 1. So no longer do we care about the one who's closest to 1, but the one whose residual after multiplying by m is closest to 1. Okay? So our goal is to have, for random m, we want an equitable additive power method. So what we want is this, that when we take u and raise it to an mth power, the eigenvalues kind of mix around, such that when I just strobe it on this kind of very thin funnel, I get exactly a uniform random eigenvector. So you can think of this as kind of this lottery machine where you rotate your balls, and then when you stop, the guy who's closest to the exit just falls out. You want this to be a random thing. Okay. So how do we enforce uniformity? Well, we want the eigenvalues of u to the m to scatter around the unit circle kind of at random. So how do we treat this formally? Well, luckily for us, there is the theory of low discrepancy sequences. So Erdős and Turan introduced in 48 a property that looks at how well a sequence behaves in space. So we look at an S-dimensional sequence of length m, and we look at all the sets of hypercubes in 0, 1 to the s. And for each cube, we look at its indicator function, whether a point is inside or out. And then we define the discrepancy of the sequence as follows. We look at a certain hypercube, and we compare the fractional volume of that cube and the number of times, the average number of times that it is visited by the sequence. And we compare them, right? And then we take the worst case. So it's the worst case deviation between the number of times the sequence visits a cube compared to its volume. That's the discrepancy of a sequence. The cute thing about this is the following interpretation. If you have a sequence of low discrepancy, say S-dimensional discrepancy, and you look at any set of S coordinates, then this kind of vector x1 of m up to xs of m is very close to a uniform, to a bunch of independent uniform random variables. So that's the key interpretation. So low discrepancy is kind of the same as saying it's a bunch of IID random variables up to some total variation error. So what will be our sequence? So we're given an arbitrary Hermitian matrix A with these eigenvalues. And we fix some integer m. And now we look at this sequence. S sub m of A is the following. We look at the fractional part of the eigenvalues, then the fractional part of twice the eigenvalues up to fractional part of the m times the eigenvalues. It's a sequence of dimension n of length m. And now our goal is to show that the discrepancy of this sequence is inverse polynomially small. If that's the case, then our algorithm would work, right? Because we can filter out, given a random m, kind of a uniformly behaving eigenvector. So that's the goal. OK, so we want the n eigenvalues to be approximately IID. So if we're looking at a sequence of dimension s, we want to set s equal n's, right? That would be kind of the best situation. Unfortunately, there's a believable conjecture in this field that has been proven only for s equals 2, which says the following. If you have an s-dimensional sequence of length m, your discrepancy scales up exponentially fast in s. So that's not good, right? Because our s, if it's s equals to n, we need m to be exponential. Then our complexity kind of jumps by another factor of n. So we can't achieve n-wise independence for m equals polynomial in n. So what we do is we relax this condition. We show that even if your sequence has low discrepancy only in pairs, in other words, it's approximately pairwise independent, only then, even if that's true, then you still get your goal. It still outputs a random unit eigenvector. OK. So how do we get pairwise low discrepancy? Well, we're still not there. Suppose you get a matrix A, which has these eigenvalues, 1, 1/2, 1/3, 1/4, and so on. So we want every pair to have kind of a marginal which is kind of uniform. But this is not the case. Look at even the first pair, 1 and 1/2. If you take the residual of integer multiples, you get they're either collocated or antipodal, depending on the parity of your integer. That's very far from what we want. OK, so given A, we don't want A. We look at a nearby A, and we want the discrepancy of the nearby A to have to be low. OK, so a natural solution would be to perturb the matrix with some Gaussian matrix. OK, so instead of looking at arbitrary eigenvalues of an input A, we get random eigenvalues of A prime. So what is the discrepancy of a sequence with a random seed? OK, so there's some good news. There's a theorem by Niederreiter that shows that if you take points on the m grid of the unit circle, you have m points, and you select them uniformly at random, and you look at the discrepancy of that sequence, it's log of m to the s over m. So now s is 2, m is polynomial in n. It seems that we're pretty good. Unfortunately, the perturbed eigenvalues play the role of these uniform points. And if we need them to be uniform, it means our perturbation needs to be super strong, and we lose all connection to the input. So that's no good. So what we need to show is a weaker, kind of more relaxed version. What we show is that to achieve low discrepancy, you don't need your initial C to be uniform on the entire 0-1 grid. They can be uniform independent on very, very small intervals, so long as they're kind of not too small, not exponentially small. Inverse polynomial small is OK. And we still get that the discrepancy of a typical sequence is still pretty low. So we use this kind of lemma that we've shown in the theory of low discrepancy sequences. And then what we do is we show that actually adding a small Gaussian perturbation gives you the result. So why is that? You have a matrix in which the eigenvalues are pretty well spaced. And under this assumption, if you add a GUE matrix, a Hermitian Gaussian matrix, what happens is the eigenvalues kind of behave, or misbehave, like independent Gaussian variables. And if that's the case, we can apply our lemma from before and conclude that if we take these perturbed eigenvalues, multiply them by integers, take the fractional part, that behaves like a sequence that is almost random in pairs, independent random in pairs. OK. So, but wait a minute, I said that the eigenvalues are well separated. That's typically not what you get, right? So the solution is to blast the initial matrix with another perturbation, a stronger one. Fortunately, a theorem by Nguyen, Tao, and Vu from 2015 shows that this is actually enough. If you take a matrix A, you bombard it with a small GUE matrix, then what happens is the eigenvalues tend to scatter. They have at least a minimal spacing with high probability. And in fact, this already gives us the algorithm. You get in the matrix A, you add to it a small Hermitian Gaussian perturbation, you scatter the eigenvalues, and now you apply many, many copies, where in each copy you add another tinier perturbation to cause everything, all the randomness to kick in and spit out an independent uniform random eigenvector. So that's the entire algorithm. So step A perturbs the matrix, and all of these run in parallel. And that's it. So to sum up, so there's a way to take quantum phase estimation and turn it into a classical algorithm for spectral decomposition. It is inherently parallel because we're doing eigenvector sampling independently. And it's also inherently stable because we're using unitary matrices. So we get both of them for free. There are some open problems that we want to address. One of them is, can the runtime be improved to n to the omega? We think it can be done, but we haven't been able to show this. And can we do away with less randomness? Right now, we need like O of n squared random bits. Maybe we can do just perturbation on the diagonal or close to the diagonal and get away with it. And finally, can we find other uses for eigenvalue ergodicity? That may be an important question because this kind of field has not been connected to linear algebra. We hope that this connection becomes more fruitful. Maybe in the context of the previous talk that was presented here, maybe there are some other ideas that can come into play. Thank you.
Any questions?
Logarithmic many terms.
So then there's, in that case, like, there's some natural interpretation of this as like, you're essentially just adding together the powers of your matrix, and it seems like it's magically doing it.
Well, you're approximating the unitary matrix by a truncated Taylor expansion. And yeah, I mean, everything kind of follows from that. Yeah, it's true, like, this is kind of like the way we think about stuff in quantum, right? Because we usually talk about the unitary matrix and not anything else. So yeah. So essentially, everything is kind of as hard as matrix multiplication over unitaries, right? For example, this is like relates to your talk, right? If you can multiply two unitary matrices in faster time than n to the omega, then everything kind of goes down here.